Hello everyone, I hope you're doing well. In this video, we are going to solve problem 27 from chapter 1 of solid state physics by M.A. Wahab. Let's see the problem statement and we'll dive directly into the solution. So the statement says that show that the HKL plane is perpendicular to the HKL direction in cubic lattice. So we can see here that these are the Miller indices of plane. Okay, I have just underlined them. This is not something unusual. It was HKL. Okay, I just underlined them to highlight them that they are equal. You can see we have same Miller indices for plane and similar Miller indices for the direction, and we need to prove that all those directions and planes which have similar Miller indices are perpendicular to each other. That is what we need to prove, in other words, if we want to understand it well enough. So let's see how we can do that and quickly jump into the solution part. So the proof is really simple, and let's see. We are given with a plane with Miller indices H, K, and L. Okay, these are the Miller indices of the plane, and how we can find out the intercepts from these planes. All right, so let a plane HKL inside a cubic unit cell with lattice parameter A as shown in the figure. The figure 1. Okay, we'll draw this plane. Okay, we'll draw this plane inside a cubic unit cell whose lattice parameter is A, and I have just mentioned it in here to show you people that I'm gonna draw this plane inside a cubic unit cell. So the first thing that we need to calculate is the intercept that this plane makes with the x, y, and z axis. So let's calculate those intercepts, and I'm gonna construct a table that I always do because it looks presentable, and you are supposed to do this step in exam because it's important. So here I'm going to mention the indices of plane. Okay, we are considering plane here, not the direction, so keep that in mind. H, K, and L, these are the Miller indices, and we need to calculate the intercepts. So for that purpose, what you need to do is to take reciprocal of these indices. So reciprocal means dividing it by 1, H 1 over K and 1 over L. Well, these are the reciprocals only, and since we are considering the general case, we need to incorporate the type of structure you are considering. Like we are considering the cubic crystal structure or cubic unit cell, and for that purpose we need to multiply the lattice parameter that the unit cell has corresponding to x, y, and z direction, and hence we will be multiplying A with x intercept, A with the y intercept, and A with the z intercept to show that it is a cubic unit cell. Alright, this step is critical for this proof. Okay, if you don't do this, your proof is wrong and insufficient, because fractions alone doesn't tell you anything about the lattice in which the plane exists. Okay, in which this plane with Miller indices HKL exists. Okay, so you need to incorporate that step in which you are multiplying the lattice parameters to show that yeah, it's a cube. So multiplying by A, it's A by H, A by K, and A by L. Alright, so these are actually the intercepts. Multiplying with the lattice parameter incorporates and acknowledges the type of crystal structure you are considering. So if it's cubic, we are considering AAA, we multiplied with AAA. But if these lengths were different, then we need to multiply the first index by, the first fraction by A, second by B, and third by C, because in some other crystal structures the lengths are unequal, so we need to multiply by that. So for that purpose we are doing it like we need to multiply them. If it would have been any other lattice, then the situation and the results would have been different. I hope that is enough. So now we have got the intercepts, and we can see the intercepts that we have got. It's a by h as x-intercept. This is x-intercept. Then we have a by k. This is the y-intercept. And a by l. This is the z-intercept. Let's draw this plane inside the cubic unit cell. Alright, so we are drawing a cube, joining these together. This is x-axis, this is y-axis, and this is the z-axis, and here is our origin. Now x-intercept is actually a by h, so we randomly selected any point. Okay, this is a random position on x-axis. Okay, x-intercept is always lying on the x-axis, so I randomly choose this point. Let's say this is a by h. Okay, this is x-intercept. Now we have y-intercept, which is a by k, so I randomly chose this point. Let's say this is a by k, and this is the x-axis, and on x-axis I'll randomly choose some point, and let's say it is a by l, h k l. So the order is same. Now we'll join these lines, these points together, and it forms a random plane. All right, we can see here this is a random plane, and we can even shade it, but that is not needed, but we can shade it. Now you can see here that this plane is made up of 3 boundary lines. Okay, there are 3 boundary lines, and let me call these points as A, B, and C. This is, let's say, capital A point, this is capital B point, and let's say this is capital C point. All right, we just named them, and here this plane is made up of 3 vectors, okay, which keeps on repeating themselves, okay, in 2D, so that it makes up the whole plane. For example, what I want to mention in here is the fact that, let's say this is a triangle. Okay, these are 3 different vectors, boundary vectors. Now if you repeat these boundary vectors, okay, like that, so that they are really closely spaced, if you repeat them with infinitely small spaces in between them, then you get a plane. That is how you get a plane. Okay, if these vectors are really closely connected to each other, then you get a plane. It means that the plane is actually made up of infinitely many parallel vectors, which are defined by these, whose directions are defined by these boundary vectors. All right, what I'm trying to say is that we have actually 3 vectors in here, and let's say this is one of the vector. Direction doesn't matter, you can choose random direction, and I'm using like this kind of direction. This vector is in here, is in this direction, is in this, and it's this. You can choose this direction, this or this, whatever. It's just random and arbitrary. What we are gonna do in here is that we have 3 different vectors, B to C. This is BC vector, then we have CA vector, and then we have AB vector, and these 3 vectors actually defines this plane. All right, and if the direction HKL, if this direction is perpendicular to BC vector, AC vector, as well as AB vector, okay, if this direction is perpendicular to all these 3 directions which defines the plane, then the direction HKL is perpendicular to the plane that is defined by these 3 vectors, or we can say that the plane is perpendicular to the direction. Okay, so that is how we are gonna do that. And yes, we'll be using the scalar product of vectors, because I must tell you that in physics and mathematics, whenever you are required to prove the orthogonality or perpendicular nature of 2 vectors, states, wave functions, cats, or whatever it is, scalar products always help. Okay, scalar product of 2 orthogonal vectors or two perpendicular vectors is always 0. So that is the property that we'll be using in here, that we'll find out the vector for BC, the vector for CA, the vector for AB, and the vector for the direction. And we'll find out the dot product of direction with BC vector, with AC vector, and with AB vector. And we'll see that if all those scalar products are 0, then the direction is perpendicular to this plane. They should all be 0. If any of it is non-zero, then it means the direction is not perpendicular to the plane. Okay, that is how we are going to do that. Let's do it. So first of all, this is the necessary figure that you are required to draw, and even you can draw the direction and it will look like that. Okay, and you'll write HKL because it's a random direction. This is how you are supposed to draw it. Now let's find out the BC vector. Here the BC vector is given by the coordinates of C minus coordinates of B. Okay, so what are the coordinates of B, C, and A? Let's write down their coordinates. So coordinates mean the motion starting from origin that you have to make to reach that point. So starting from origin, I'll have to move A by H to reach this point B, because x-intercept is actually the point. This is the point, right? And this is x-intercept, which means that it's the value of x, and it's A by H. So I have to move A by H to reach that point, and none of the motion along y and z direction, so it's 0 and 0 along y and z. All right, I hope you are clear about the concept of intercepts. Intercepts are the point on a axis line, so it's the x point, this is the y point, and this is the z point. And in intercepts, only the axis to which this intercept is non-zero. All of the other parts or dimensions would be 0 in here. For example, in x-intercept, y and z motion will be 0. In y-intercept, x and z motion will be 0. In z-intercept, x and y motion will be 0. That is how you interpret it. So here we have 0, a by k, as I told you, and 0. X and z will be 0, and a by k is actually the y point, and you have to move only that unit to reach that point. And similarly here, it's z point, so 0 for x, 0 for y, and a by l is the z-intercept. So these are the coordinates. Okay, and if you put I hat, j hat, and k hat with them, I hat, j hat, and k hat with them, you'll get these vectors. So let me first do that thing. Let me write these vectors. So let's write a vector, which is 0 I hat with x, j hat with y coordinate, and k hat with the z coordinate. Okay, so 0 j hat plus a by l k hat. Since they are 0, so we don't need to write them. A is simply a by l k hat. All right, next we have b vector, which is a by h I hat, j hat, and k hat are the unit vectors. 0 j hat and 0 k hat, we don't need to write them. Okay, so this is it. Then we have c and 0 I hat plus a by k j hat. We don't need to write the 0 one, so a by k j hat. Now let's find out the bc vector. Bc vector, that is equals to bc, b to c, so we always minus the final from initials, so final point minus initial point. C vector, which is this a by k j hat, minus b vector, which is a by h I hat. This is bc vector. We'll be using it, all right, later. Let's write the AC or CA, that doesn't matter. Whatever pattern or order you are using, that doesn't matter in here. So C minus A, C is A by K j hat minus A, which is A by L k hat. This is AC. Then let's calculate the last one, which is AB, which is final minus initial, final point minus initial point, final minus initial. So B is, where is B? A by H I hat minus A by L K hat. This is AB. Alright, so we have calculated these vectors which are making up this plane, and now we need to write down the direction vector, and after that we'll be carrying out the scalar products. The direction D arrow over it to show that it's a vector with Miller indices HKL is given by, that is really simple. D direction is first index, which is H, then I hat, plus second index, which is K, then J hat, third index, which is L, then K hat, and we'll multiply it with the lattice parameter to show that it's a cubic unit cell. Okay, if it would have been any other unit cell in which the lengths are different, then you have to multiply H by A, K by B, L by C. But since it's a cubic unit cell, you'll multiply all of them with similar lattice parameter, which is A. So we can write it like that: HA I hat KA J hat plus LA K hat. Alright, so this is the direction D. Let's call it as 4. Now if D with HKL Miller indices is perpendicular to plane with Miller indices HKL, then the dot product of D HKL, which is actually given by 4, with the vectors that we have calculated, which is BC, AC, and AB, should be 0. Dot product, or we can say the scalar product. Okay, we have write down a strategy that we'll be following in order to prove that whether they are perpendicular or not. So that is the strategy. Now let's find out the dot products now. So first we'll find out the dot product of D with BC vector. Let's do that, and first we'll write D, and here order doesn't matter as well. You can write BC first and then D, that's totally fine. But in case of vector product, the order matters, but not in scalar product. This is the D vector dot BC vector, which is A by K J hat minus A by H I hat, by K J hat minus A by H I hat. So while finding out the dot product, what we do in here is that I hat term multiplies with the I hat term, J hat term multiplies with the J hat term, and K hat term multiplies with the K hat term. So let's assemble them together. Let's write it in order. So first I write the I hat component, which is minus A by H I hat. Then I'll write the J hat component, which is A by K J hat, and since there is no K hat component, which means that it's 0 K hat. Now let's multiply them together, HA with minus A by H. Okay, because I hat will multiply with the I hat, then J hat will multiply with the J hat, so KA into A by K. During multiplication, you are not supposed to write these unit vectors because they become 1. Okay, that is the property of dot product. You don't need to do it right here. Okay, so then LA multiplies with 0. Let's simplify them together. It's H cancel, and it's A into A minus A square. Then k cancel, plus a into a is a square, plus la into 0 is 0, minus a square plus a square, that is 0. We can see that first dot product is 0. Now let's do the next one, which is d dot ac. Let's do that. HAI hat plus KAJ hat plus LAK hat dot AC. What is AC? A by KJ hat, KJ hat minus A by L K hat. Let's find out the dot product, and here we can see that there is no I component, so we can write in place of it 0. We can write 0 in place of it. 0 I hat plus a by k j hat minus a by l k hat. All right, so I hat components will multiply with I hat components. So HA into 0 is 0 plus KA into A by H. Sorry, it's K. A by K plus minus minus LA into A by L. K cancel, L cancel, A is A square minus a is a square minus a square is 0. So we can see that second one is also 0. Now let's see the last one, d dot ab vector. HAI hat plus KAJ hat plus LAK hat dot then AB vector, which is A by H I hat minus A by L K hat. Okay, now let's multiply them together. I hat will okay, we don't have j hat in here, so we need to write 0 in place of it. Zero j hat minus a by l k hat. So I hat component will multiply with I hat component HA, then A by H plus z plus 0 I was saying, ka into 0, which is 0, then plus minus minus la into a by l. All right, so if you are thinking that what happens with these unit vectors, it's like I dot I, which is equals to 1, j dot j, which is equals to 1, k dot k, which is equals to 1. Okay, they become actually 1. That is why we are not mentioning them. H cancels and a square minus l cancel, a square, which is 0. All right, so in this way we have seen that all these dot products are 0 since d dot bc, d dot ac and d dot ab are all 0. Therefore d is perpendicular to bc, ac and ab. We are just elongating our statement. We are not just writing it direct way. We are, elongating our statement. So we can now say that hence the plane HKL is perpendicular to the direction, perpendicular or orthogonal to the direction HKL in cubic unit cell. All right, and you'll see that if you do it for the other unit cells in which even where a, b and c are the lattice parameters, then you'll see that they are not equals to 0. And in that case, for those unit cells in which the lattice parameters are not equal to each other, d vector is not perpendicular to the plane with similar Miller indices. Okay, so it's only true in cubic unit cell. and we have proved it. I hope it's clear to you people. Take care. Goodbye. Yeah.